In this lesson, we are going to learn energy carried by electromagnetic waves. And you will be able to explain the energy carried by electromagnetic waves after this lesson. Now, as you see, here is a electromagnetic field propagating in this direction, and this is y direction, and there is an oscillation of the electric field in the z direction, and also there is the oscillation of the magnetic field in the x direction. Okay, the electromagnetic waves carry energy, and as they propagate through the space, they can transfer energy to objects placed in their path. Now, assume here is an object placed in front of the electromagnetic wave. So when the electromagnetic wave, when it strikes this surface, and there is charges in the surface, there are charges in all objects, and when the changing electric field and changing magnetic field reaches to this surface, they affect the charges here, and the charges here start oscillating, and the surface is heated up. Let's start learning energy density to learn the energy transferred by electromagnetic waves. So the energy density is the energy per unit volume, and the instantaneous density associated with the electric field is equal to 1 over 2 epsilon 0 E square. Here, E square is the electric field, and epsilon 0 is permittivity, and it's equal to 8 times 85 times to the negative 12. And on the other hand, the instantaneous energy density associated with the magnetic field is equal to B square over 2 mu 0. Mu 0 is the permeability, and it's equal to 1.26 approximately times 10 to the negative 6. Where this energy density is coming from, let's calculate, for example, the energy density associated to the electric field by looking at the energy stored in a capacitor. Now we know that if we have a parallel plate capacitor, something like this, it will have an area, and there's going to be a distance between the plates, and the electric field lines are going to be like this from the positive plate to the negative plate. Now we know that the energy stored in a parallel plate capacitor is equal to 1 over 2 C V square. V here is the potential difference, and this is V square. C is the capacitance. And now we know that also the capacitance of a parallel plate capacitor is C equal to epsilon 0 A over D, and also it is connected to a voltage source. Assume it is connected to a voltage source of V plus minus, and V is equal to E times D. E is the electric field between the plates, and D is the distance between the plates. So now here we know that the energy stored will be equal to 1 over 2. Instead of C, I'm going to write epsilon 0 A over D times V square is going to be E square D square. Okay, so this D and D cancel each other, and we will get 1 over 2 epsilon 0 times E square times A times D. A is the area, D is the distance, and A times D gives us volume. Let's write volume like this. So the energy is equal to 1 over 2 epsilon 0 E square divided by volume. Now we know that the energy density is going to be equal to energy divided by the volume. So if we write this volume to here, then this equation is going to be equal to 1 over 2 epsilon 0 E square. So as you see, the energy density is equal to this. Similarly, you can prove that the energy density for the magnetic field is equal to B square divided by 2 epsilon 0. Now let's calculate the speed of light by considering the energy density. Now when the wave is propagating, when the electromagnetic wave is propagating in a space, for example here, the energy density associated with the electric field and associated with the magnetic field are going to be equal to each other. That's why we can write UE equals UB. They are going to be equal to each other. And we know that for the electric field it is 1 over 2 epsilon E square equals, for the magnetic field it will be B square over 2 epsilon 0. Okay, the energy density of the electric and magnetic fields are going to be equal to each other. So from here, let's make some mathematical calculations. I'm going to write epsilon 0 mu 0 here, and it will be equal to 2 and 2 are going to cancel, and it's going to be equal to b square over c square, e square. And on the other hand, we know that E over B is equal to C. So it means that E square over B square will be equal to C square. Now here, this is B square over E square. So it is going to be equal to 1 over C square. So let's write epsilon 0 mu 0 is going to be equal to 1 over C. And if 1 over C square, sorry. So if we rearrange this formula, C is going to be equal to 1 over epsilon 0 mu 0. Now we know the value for the epsilon 0 and mu 0. If we insert their values here, approximately we will get 3 times 10 to the 8 meters per second. So let's continue with the energy density, and now the total energy, the total instantaneous energy density U is equal to the sum of the energy densities. The total instantaneous energy density U will be equal to total U total. This is the total instantaneous energy will be equal to the energy or density of the first one, epsilon 0 E square plus B square divided by 2 mu 0. Now in this formula, if we know that C is equal to E over B, okay? So instead of E here, we can write that E is equal to CB, okay? So when we write E is equal to CB, U total will be equal to 1 over 2 epsilon 0 C square B square plus B square divided by 2 epsilon 0. Okay, now simplifying this equation will give us B square divided by epsilon 0. If we do a similar analysis for the U total, similar calculations here, instead of E, I wrote E is equal to C over B. But also we can write B is equal to E over C. Here, if we write, instead of B, we are going to write E over C. Let's write the equation. It will be 1 over 2 epsilon 0 E square plus, instead of B square, I'm going to write E square divided by C square times 2 times mu 0. So then, simplifying this equation will give us epsilon 0 times E square. So as you see, the total instantaneous energy density is either equal to this one or it is equal to that one. Now what about the total average energy per unit volume? Let's divide this space, and the total average energy will be equal to this is the changing instantaneous energy. This is also the changing instantaneous energy, but the average energy, the changing energy is going to be something like this. It is changing. Since it is square, the total instantaneous energy density with the time is going to have a changing behavior. When we are looking at the average value of the total, we are going to use, if this is the maximum value, this is the maximum value. So the average energy density, total average density is going to be, this is the changing one, it will be the half of the maximum. The average, this average is the half of the maximum. Here is the maximum and the half of it. So then we can write this average instantaneous, not velocity, the energy density will be B max squared divided by 2 epsilon 0. It is half of the maximum value. Or U average can also be written as it is equal to epsilon 0 E max squared divided by 2. Let's look at power in electromagnetic waves. The energy flow of electromagnetic wave is described by the Poynting vector S. And why we call it the Poynting vector? It is named after the English physicist John Henry Poynting. In 1884 he deduced this formula. For the power, now think electromagnetic waves are propagating, okay, and assume now they strike a surface. Here is the surface of area A, and let's have this volume of electromagnetic waves. From here to here, they are propagating with velocity c, and in time delta t, they are going to cover this distance. How much energy is in this volume? All this energy is going to be transferred to this area, and some power will be delivered to this surface. So the amount of the energy carried in this volume will be equal to the density of the energy times delta volume. And what is the volume of this space? It will be equal to, first of all, energy density. Remember from our previous calculations was one of them was epsilon 0 times E squared. This is, by the way, average energy density times delta volume. Here will be, this is going to be the distance, c times delta t times a. C times delta t times a. Now let's calculate the Poynting vector. It is the energy delivered to the, energy delivered to the area per second. So we are going to have the energy delivered per second to the area. That's why this is going to be energy divided by delta t is the power, divide by area. So it is going to be equal to, instead of delta v, I'm going to write this formula, epsilon 0 E squared times c times delta t times a, divide by, here we have delta t times a again. A and a, delta t and delta t cancels each other. We have epsilon 0. We will left with epsilon 0 E squared times c. This is the energy, this is the power delivered to the surface. We can calculate the Poynting vector also if we, instead of energy density, if we write b squared over epsilon 0, here we wrote the energy density associated with the electric field, but if we use the total energy associated with the magnetic field and do the similar calculations, and we are going to write something like this. Instead of u, I am going to write b squared divided by mu 0 times c delta t times a, divided by the a times delta t. So simplifying this equation will give us c times b squared divided by mu 0. So this is the power delivered to the surface. These equations for S apply at any instant of time and represents the instantaneous rate at which energy is passing through a unit area. The SI unit for the Poynting vector, the power delivered to the surface, is joules per second meter square or watt per meter square. Let's look at the intensity. The average power per unit area, we will call it intensity, it is transported by electromagnetic wave, is half of the peak power. Now, the power, I'm going to now express the average intensity will be equal to, in terms of the in terms of the energy associated with the electric field. Remember, we found it from the Poynting vector, we found it as epsilon 0 E squared times c, but this is the energy which is a changing energy. Here electric field is changing. We are now going to locate the average power. In this case, I explained that the average is equal to the half of the maximum. So here I'm going to write c times epsilon 0 E max squared divided by 2. This is the average power per unit area. Also remember, for the magnetic field, I'm going to write, we found that the S was equal to c times b squared divided by mu 0. So this is the changing Poynting vector. Now the average will be equal to the half of the maximum. It will be c times b max squared divided by 2 mu 0. Okay, so if a source with power P source, assume if there's a source and its power is P, if it emits electromagnetic waves uniformly in all directions, the electromagnetic wave intensity at a distance r from the surface is going to be I is equal to P source divided by 4 pi r squared. Here is the power of the source. Assume it is emitting electromagnetic waves to all directions at a distance r from the source. The amount of the intensity I at this point will be P divided by 4 pi r squared. Now let's look at some examples. The first example is, what is the magnetic field amplitude of an electromagnetic wave whose electric field amplitude is 12 volts per meter? Now we know that there is a relationship between the magnetic field and electric field. C is equal to E over B. Okay, so from here we are asked to find the amplitude, the electric field amplitude of the electric field. So E max will be equal to C times B max. I'm sorry, we are asked to find B max. What is the magnetic field amplitude? So from here, B max will be equal to E over C, E max over C. So it will be equal to the maximum value of the electric field is given as 12 divided by 3 times 10 to the 8, and this will be equal to 4 times 10 to the negative 8 Tesla. As you see, it's a very small amount of magnetic field. Second question. A cell phone broadcasts a 0.5 watt signal at a frequency of 2 gigahertz. What are the amplitudes of the electric and magnetic fields at a distance of 10 centimeter? This 10 centimeter is approximately the distance from our ear to our brain. We are going to calculate the amount of electric and magnetic field at the location of our brain. Now remember that I told you that the intensity of the electromagnetic waves varies with the distance as P source divided by 4 pi r square. This will be equal to the power of the source is 0.5 divided by 4 pi times r is 0.1 meter square, and it will be equal to 7.96 approximately watt per meter square. Now remember, for the intensity, for the average intensity, we found that it was equal to C times epsilon 0 E max square divided by 2. From here we are going to find the maximum amount of electric field at 10 centimeter distance. So if we rearrange this formula for E max, it will be equal to 2 times intensity divided by C times epsilon 0 square root. If we plug in every term, it will be 2 times, here is the intensity, 7.96 divided by C is 3 times 10 to the 8 times epsilon 0 is 8.85 times 10 to the negative 12 square root. In calculating this value, it's going to give us approximately 60 volts per meter. Similarly, not similarly, but how can we calculate B max? B max is equal to E max divided by C. And we know E max, it is approximately 60 divided by 3 times 10 to the 8. So this gives us approximately 2 times 10 to the negative 7 Tesla. So the energy, the amplitude of the electric and magnetic field, here the electric field is 60 volt, and here this is 2 times 10 to the negative 7 Tesla. So electric field is much more effective than the magnetic field in this case. The last question. A certain microwave oven projects 900 watt of microwaves onto a 0.1 meter square area. First, what is the intensity in watt per meter square? The intensity I average is equal to P over A. And P is 900 watts divided by 0.1. This will give us 9,000 watt per meter square. B, what is the peak electric field strength? And this is the average value of the intensity. But to find the to find the maximum intensity, it will be 2 times I average. This is important. So I max, the maximum value of the intensity, will be equal to 2 times 9,000. So it will be 18,000 watt per meter square. Okay, so let's find the electric field, maximum value of the electric field. E max will be equal to 2 times intensity, maximum value of the intensity, divided by C times epsilon 0 square root. And this is going to give us 2 times 9,000 divided by 3 times 10 to the 8 times epsilon 0 is 8.85 times 10 to the negative 12 square root. And in calculating this value, we will get approximately 26 times 10 to the 2 volts per meter. This is the value of the electric field. What about the magnetic field? For the maximum value of the magnetic field, I'm again going to use E max is equal to B max is equal to E max divided by C. It will be 2600, this one, divided by C is 3 times 10 to the 8 meters per second, and this will give us approximately 8.68 times 10 to the negative 6 Tesla. Okay, thank you for listening. This is the end of the lesson. See you next time.